My name is Markus Preising, and I'm in choroideremia research and patient support since 1992, when choroideremia was identified as a second gene of inherited retinal disorders. Before we can start, we need to talk about some definitions. Nowadays, the disease is called choroideremia. In former times and elder references, you may find the expression tapetochoroidal degeneration, which refers to the fact that in choroideremia, the patients lose the retinal pigment epithelium, RPE, as well as the retinal structures. And therefore, this definition of tapetochoroidal degeneration is a pure description of what you see when you do a funduscopy. The underlying gene is a CHM gene. In elder references, it may be referred to as the RAP1 gene, and the RAP1 at least refers to the RAP escort protein as the gene product of the CHM gene. A patient that is referred to you will present with large areas of depigmented fundus, which is due to the loss of the retinal pigment epithelium. Wherever this depigmentation occurs, you can look directly through to the choroidea and see the translucent choroidal vessels in the fundus. The fundus has some remnants of pigmentation, and the size of these pigmentations versus the size of the depigmented areas gives you a good overview of how well processed the disease is. To give you an impact of this depigmentation, you may use fundus autofluorescence imaging. In fundus autofluorescence imaging, you may see large areas of reflections of what you may identify as fundus autofluorescence, but these large areas are in fact nothing else than the reflection of the light from the sclera. The autofluorescent areas are more strongly shining and may occur hyperfluorescence, but in fact, this is only the standard fluorescence you have in the remnants of the retinal pigment epithelium in these areas. When you pass on, your next step would be to check the patients with a retinal optical coherence tomography. And from this patient, this very young patient, we have a look on here, you will find that the retinal pigment epithelium is lost, and only in the area of the macula you have remnants of the retinal pigment epithelium. Above this retinal pigment epithelium, you also lose the photoreceptor layers. And so, in fact, patients where you can see through onto the choroidea, then you have lost, in fact, all the structures you need to have vision, at least. So the fact is, in choroideremia, you have lost photoreceptors and retinal pigment epithelium, and only few areas of retinal pigment epithelium may be left at last. We need to talk now about the stratification of the retina. And in these images, you can see that the stratification of the central retina may be preserved. This is a different patient. He has some photoreceptors left. He has some choroidea, of course, and some retinal pigment epithelium right in the center of the retina, which gives him a vision that might be well preserved over a longer time. The inner retinal layers in this patient are also well preserved, but in the periphery you will lose the fractional structures very completely. Here in this infrared image you can see the areas where you have lost photoreceptors and RPE, and in the central area where RPE and photoreceptors are more or less well preserved. As we now saw that the photoreceptor layer is lost in these patients, we need to have a look at some special findings, especially the rosettes you can see in the OCT images. And if you have a histology, which has nicely been done by Ian MacDonald in a previous publication, you see that it is a curling of the retina and the retinal cells, the photoreceptor cells, which are with the photoreceptor outer segments inside of these curls and the nuclear areas surrounding these curls. In fact, this is also a very late state of the disease, and the function of these photoreceptors is very questionable. What does it mean to the patients? These patients usually report to the clinic by telling you in their early adolescence or in the late adolescence that they cannot really go well in ball games because they do not see the ball coming in. They have problems in night vision from early ages on, and you will find them being hampered to have a full visual field. Here in this patient you can see the development of the visual field, which over 2 years can decrease inside with a smaller targets, and over a long time you will have the loss of the visual field. That is due to the loss of the photoreceptors, especially in the periphery, but also progressing into the center. Electrophysiology is a good technique to help you identify these patients. As it is a loss of especially the rods, you will lose photoreceptor scotopic and photopic responses in electrophysiology in the Ganzfeld ERG. And as you can see here, the sound example on the right side, both eyes, you have lost the A wave and the B wave compared to the normal responses of the electrophysiology testing. Very important for the patients is the development of the visual acuity. As you can see here, this is a summary of 38 patients we have tested over several years, and you can see that the patients lose vision. This is in decimals. On the left side it's in logMAR, and the patients with a progressing age are going down to a visual acuity of 1.0 logMAR, which is 0.1 decimals, but usually they do not go very much below that. In the younger ages, the visual acuity can be quite well and quite stable, but by the age of 50, each of the patients usually experiences a strong loss of visual acuity. Very strong loss of visual acuity is quite rare in these patients, as well as even in later ages, a complete loss of visual perception. To visualize this visual function, the visual acuity, you may have multifocal ERG recording on these patients, and as you can see, these patients quite early have lost potentials of correlated potentials in the center of the macula, and which is a very clear indication of the affected photoreceptors. It has, in this case, the cones in the macula. So let's talk a bit about inheritance in choroideremia. Choroideremia is an X-linked chromosomal inherited disorder. Here is a unusual large pedigree of choroideremia patients, as most of you experience. The families that will be reported to you are much smaller, usually of the size grandparents, parents, and some children. But what you experience is there is no transmission from man to man because of the X chromosomal recessive inheritance. But the disease may run through the female descendants and at the end come up in an affected male. The problem here is that the affected males carry only one X chromosome. This is the sister chromosome for the X chromosome is the Y chromosome, which is necessary to have as a male, because if you don't have a Y chromosome, you cannot be a male. So every male has only one information for the choroideremia gene, and if this information is in anyhow changed, hampered, or destroyed, the disease will develop. In addition, females have two copies of the choroideremia gene, so they have two informations, and some of them can cope with that by having the second X chromosome providing sufficient information and function to cover the activity of the choroideremia gene product. But even though these females have a second functional copy of the choroideremia gene, these females do not, these females are not free of specific features that define them as a carrier of the choroideremia gene failure, choroideremia gene mistake, because the activity of the change of the altered choroideremia gene belongs to the activated copy of the X chromosome in these females. Therefore, you will always find several persons inside a pedigree. You find the primarily affected males because they do not have a second normal copy of the choroideremia gene. You find here asymptomatic carriers, which are mostly present in a pedigree. You find the transmission by each sex, male to female, female to male, but not affected males, because males do not have the X chromosome from the father, from the affected father, but all daughters are obligate carriers, because they can only receive altered X chromosome from their fathers. So finally, this means sons of affected males are always healthy. But why do we have affected females in such a pedigree? We have to face the fact that in very early embryonic development, a cell decides which of the two X chromosomes will be active throughout the descendants of this cell. That means, just by chance, in each cell at a very, very early stage of the embryonic development, one of the two X chromosomes will be silenced. If you silence an X chromosome with a functional copy of the choroideremia gene, all the descendants will have a non-functional copy of the choroideremia gene, and so all the descendants of this cell will not be able to produce the choroideremia gene and the choroideremia function. If you silence a cell or a copy in a cell with non-functional choroideremia gene, all the descendants of the cell will only have a functional copy, and the function of the choroideremia gene will be present in these cells. And since it is by chance which of the two copies will be silenced, you will have a lot of combinations that may occur in a female. You can have combinations with many cells not being able to possess a functional copy, or you can have females with many cells being able a functional copy. And between that, you have all kinds of combinations. So if you now imagine that such a mosaic will be present inside the retina and inside the retinal pigment epithelium, you can imagine the more cells you have with a functionally impaired copy of the choroideremia gene, the more RPE cells will get lost, like in males, and the less cells you have with expressing the functional impaired copy of the choroideremia gene, the more cells will be active. So females that develop the disease in a way males do will have a lot of impaired function, or of cells with impaired function, and therefore develop this disease, at least in unfortunate conditions like males. And between that, of course, you will have a full set of onset and progression of the disease in females. Usually, this is quite well balanced, and the females do not have a problem with it. But in very unfortunate cases, there will be severely affected females, even though they have two copies and at least one functional copy of the choroideremia gene. The choroideremia gene. What do we need to know about the choroideremia gene? The choroideremia gene is a very large gene, but has only a small coding sequence. This small coding sequence is distributed over 15 exons, and there is a large area of non-coding sequence between these exons. This means that there is a lot of space that can be altered by mutations, by sequence changes, and also with very large introns, you are liable to easily use large areas of this gene. Therefore, you will find that about 50% of the choroideremia variants are null mutations due to large deletions of the gene, losing several exon introns as a block and sometimes even the whole gene. The other 50% are mutations that are definitely null mutations, meaning they do not produce any function because these variants are made of stop codons, preterm stop codons, of splice site variants, and so which create copies of the gene that are not able to be translated into a functional gene product. In choroideremia, the missense mutations are usually all functional. All the missense mutations that are not functional are not really missense mutations, but do have an effect on splicing or on any other control mechanisms of the production of the mRNA message. So therefore, the few missense mutations reported in the choroideremia gene are generally not affecting the function of the choroideremia gene. Together with the choroideremia gene, which was called the REP1 gene, there is an isoform, the REP2 gene, which is on chromosome 1 and which can cover the function of the REP1 gene, but not completely. And therefore, even though the REP2 gene is able to cover some activity of the REP1 gene, the patients do develop disease if the REP1 protein does not function due to the altered CHM gene. Genotype-phenotype correlation is a weird thing here. As you can see here, if you compare all the exons, mutation anywhere, you find patients with a reduced visual acuity in very early age. If you look at patients with mutations in exon 2 or patients with mutations exon 6, you see that they have better visual acuity over the ages, but this is not a general situation, and it's just here in this small set of samples where we could try the correlation. The RAP escort protein, which is a gene product of the CHM gene, is made of 395 amino acids, and it's part of the granule transferase, which assists the granulation of RAP proteins. This protein, this gene product of the choroideremia gene, escorts native RAP proteins to their first use, and it controls these RAP proteins at their first use. The RAP proteins are very important inside the cell because they are tags. They are tagging vesicles and structures to identify their targets and are necessary to bring transport vesicles through the cells to the target they are indicated for. So Rep proteins control the movement and the interaction of these vesicles. This is a small sketch about the function of the choroideremia gene. And what you see here is that the choroideremia gene is absolutely important in controlling Rep proteins that are involved in the phagocytosis of photoreceptor outer segments. As you may know, the photoreceptor outer segments are shed daily. About 1,000 discs of photoreceptor outer segments are shedded every night and replaced in the photoreceptors. And these shedded outer segments are phagocytized in the retinal pigment epithelium, and with this you develop structures called, or vesicles called endosomes. In these endosomes, the photoreceptor outer segments are recycled or at least deposited in the retinal pigment epithelium, and the activity of recycling or depositing creates an impact on the retinal pigment epithelium. The recycling of outer segments is mainly for the membranes and for some protein structures, and the depositing is mainly for the vitamin A derivatives, and finally these deposits are made of A2E, which is toxic to the retinal pigment epithelium cells. So if the choroideremia gene is altered, the phagocytosis functions still, but the vesicles created upon phagocytosis are not correctly moved through the retinal pigment epithelium for recycling. And therefore, these vesicles produce toxic debris that destroys the retinal pigment epithelium. At the end, the retinal pigment epithelium cell will die, and the died retinal pigment epithelium cell is not longer able to support the photoreceptors, because retinal pigment epithelium is needed for build-up and degradation of photoreceptor outer segments and photoreceptor cell function. And so at the end, the retinal pigment epithelium that has been lost is problematic and will not be able to support the retinal structure, especially the photoreceptors. And finally, the photoreceptors in this regard will die. So as I showed you before, the important structures and the important players in choroideremia dysfunction are the Rep proteins. We have a set of more than 60 Rep proteins in each cell with different functions affecting different activities in different tissues and cell types. Important for the function of the choroideremia gene are the Rep27A, Rep7A, Rep3, which has been reported a long time ago. And what you can see here on the left is the activity of different reps in interaction with the choroideremia gene, or the choroideremia protein, the REP1 protein. These interactions are depending on the affinity towards REP1. They are depending on the half-life period of each rep, and lately the specific reaction rate of each rep. Even though Rep27A has the lowest affinity towards Rep2, it has a high reaction rate, and therefore a substitution of Rep1 by Rep2 is not fully establishing the function that is lost when the Rep1 protein is not functional. By the end, especially this Rep27A is a rep protein that mostly confers the loss of function that leads to the choroideremia disease. As I told you before, rep proteins are the major players in the disease of choroideremia, especially as these rep proteins guide the vesicles through the cell and to support functions of vesicles and structures. We have more than 60 rep proteins, and Rep27A, Rep3A, and Rep7A have been reported as the most important ones concerning choroideremia. The question at least is, how can we support the function of the Rep1 protein if it is not active anymore? And as I told you, Rep2 can substitute this function for some of the rep proteins. The problem is each rep protein has a specific affinity towards Rep1, has a certain half-life period where it is active, and has a specific reaction rate. So what we need to have is a protein that supports those rep proteins that do the similar activity of those that have these specificities towards the Rep1 protein. In phagocytosis,
Markus, I think we are blocked again because I am always on the same slide.
I didn't change the slide.
Ah, okay, great. That's good.
I'm still on the same slide. No.
Okay, good.
Yep.
Sorry.
I didn't change the slide. Rep27A is a protein that is extremely important in the phagocytosis of photoreceptor outer segment, but it has the lowest affinity towards Rep2 substitute of the choroideremia protein. Therefore, the substitution of the choroideremia protein is absolutely inconsistent, and that causes the disease in the retinal pigment epithelium. Rep1 in human RPE is therefore absolutely necessary to provide the function. If the function of Rep27A is not correctly provided in the human RPE, we have acidification of the phagosomes. We have reduced release of cytokines and growth factors, especially BFGF and VEGF, which can be shown also in blood cells as a functional assay of the rep protein. If we want to provide some therapy to choroideremia patients, we have to guess a bit about the activity of the sequence variants in choroideremia. Here we checked the expression of choroideremia mutations within the lymphocyte cells because that is simply done due to the fact that the RAP1 protein is expressed in all cells of the body. And what you can see here in a simple, very simple RT-PCR assay is that each choroideremia mutation produces a gene product. Only large deletions affecting the whole gene do not provide a gene product in the choroideremia gene. We use here a large deletion from this patient as a negative control against what, and you see you don't get a product. But all the other variants we have, either duplications, insertions, stop codons, or splice site mutations, they all produce a gene, an mRNA that can be shown here in this assay. And also in patients as well as in females. Therefore, there is choroideremia mRNA in these patients that can be used for gene therapy approaches. As these choroideremia gene mutations usually provide mRNA with a preterm stop codon. One of the latest ideas was to use atallurane, which is a drug, to overrun stop codons and produce full-length gene product. And the tests with atallurane in other diseases, for example, like Becker's muscular dystrophy, were not that successful, but this atallurane nonsense-mediated decay overrunning therapy approaches are still going on and are trying to be more efficient in these patients. The gene therapy trials that have been set up are generally trials of gene substitution. There have been several trials in this regard, which have at this time all been completed with quite inconsistent results in this regard, that the general idea of activating a choroideremia gene and producing functional choroideremia protein in photoreceptor cells did work very well. But the problem, as you can imagine from the first slides I showed in this talk, is that we have lost those cells we need to provide visual acuity and visual function. And we cannot restore these cells. Therefore, we have to consider that the outcome parameters for the choroideremia gene therapy need to be set differently than simply telling we need an improvement in visual acuity or night vision acuity. And in this regard, these latest or these gene therapy trials that have already been done all struggled with the fact that visual acuity could not be provided by the amount the authorities expected as a positive outcome of the trial. The latest The latest clinical trial that is going to start now is by Choroideremia. They do a completely different approach, and it might be one of the more successful approaches for those patients who have already lost a lot or most of their vision. Choroideremia are providing a construct, providing a drug that is activating bipolar cells, and under illumination, this drug closes channels, ion channels, and provide, by this closing of the ion channels, an nerve activity and nerve impulse that can be transmitted to the visual cortex and create an image in the visual cortex. It's a trial that is not addressing specifically the photoreceptors or the RPE, and also is requiring that the inner retina is preserved in a way, but it's quite sophisticated approach, and we are looking out to see how this clinical trial, which is in phase 1-2, will develop. On the other hand, of course, you can imagine if you have residual or preserved inner retina, you can also add optogenetics as an option, but the problem is the patients must have lost much of their visual acuity and light perception to not interfere with remnants of their visual function by providing novel and different visual function through activating the bipolar and ganglion cells. So at least if we want to develop therapies, the question is, what do FDA and EMA really expect from us? And we need to provide outcome parameters that are not too high to have a benefit of function, and we have to name outcome parameters which provide function that patients do expect from the therapy and provide a benefit for the patients, but we cannot provide, in fact, better visual acuity, but probably only increase in but only an increase in sensitivity for these patients to lower light. How can we lately quantify the gain of function, and how can we quantify the preservance of this function? Maybe we have to guess about different benefit for the clinical trials in this regard, which we have to face for the future. So this brings me to the end of my little lecture today. I thank you for your attention, and if you have questions, do not hesitate to contact me or the ERNI. We will definitely help you with all the questions you have. Thank you for your attention.